4.4 Combining Transformations, or 4.4 Continued. The last set of videos that we watched, there was only one transformation per parabola, but now you're seeing that there are several things going on at once. I want to remind us of the most helpful form in this situation: y equals a x minus p squared plus q. This is the vertex form because it gives us our vertex at p, q. I have another set of videos, so if you look at in my playlists and look at 4.4 and you see me like at the whiteboard actually talking about it, if you want to watch, if you get to this the end of this set of videos and feel like you're at a loss and you want to see a few more examples, and maybe you want to see me waving my hands in the air and making a bit of a fool of myself, you're welcome to watch those videos. But this set will follow the notes that you have in front of you very nicely. So graph each of the following equations and identify its properties. So if I were to highlight my vertex, I would say, yeah, actually let me just rewrite this so that it's a little bit more in this minus form here. So I can say y equals x minus negative 2, hey-oh, there we go, close bracket, minus 1. So what we can see is that our positive 2 and our minus negative 2 are the same thing, just as our negative 1 and our negative 1 are the same thing here. So I'm going to do these slightly out of order, but the easiest thing for me to pick out first is always the vertex. So our vertex is going to be at negative 2, negative 1. So I'm going to put my scale on and I'm going to put my vertex, close that bracket, negative 2 and negative 1. We're noticing that there's no stretch factor, there's no a. So no stretch or compression factor, so I know that it goes up in the regular way. So what I mean by that is up one, over 1, up 1, over 1, up 1, over 2, x squared. If x is 2, y would be 4. And let's see if we can go up 9. 1, 2, 3, 4, 5, 6, 7. Oh, not quite, but that's okay. We are going to draw this graph. That's a little bit of a misnomer there because it looks more like that. Okay. So our domain for all of these things is simply going to be x is an element of the reals. X can be anything from negative infinity to positive infinity. However, the range, the y, it can only cover values that are above negative 1. So y is greater than or equal to negative 1, and for good measure we can say y is an element of the reals. I just want to show you a different way. So this right here is in set notation. If we wanted to use interval notation, we would go negative infinity to positive infinity. It kind of shows the conceptual aspect of it a little bit better. We use rounded brackets when it does not include that value. And since it's infinity, you can never really include infinity because it's kind of more like a concept. It's not actually a real number. So that's why we always use rounded brackets. With this one, we would say it goes from negative 1, and it definitely holds on to that negative 1, or it definitely has that negative 1 on the graph, because that's where our vertex is. And then we say comma, positive infinity. And then we use a rounded bracket again, because it goes to positive infinity. This kind of helps us see what values x and y are, and I find sometimes it's better for domain and range. From now on, I think I'll give you the domain and range in both. So whatever you like better, you can latch onto. The axis of symmetry is where we put up that mirror. So I say it's a vertical line, so it's going to be x equals, and it is negative 2. Another way that we can get that it's negative 2, it's that p-value. X equals that p-value of our vertex, or the x value of the vertex. We have a minimum because it actually opens up, and the minimum occurs when y equals negative 1. We have two x-intercepts here. We have one at negative 3, and one at -1. So x equals -3, -1. Or we can say -3, 0, 0, and -1, 0, whichever one you like better. And we have one x-intercept, and that is going to be at 3. Oh, sorry, one y-intercept, and that is when y equals 3. Or we can write it as 0, 3. Okay, so we've graphed it using our vertex or standard form of the equation. It actually gives us a lot of good information. The only time that we wouldn't use this form here is if we didn't know the exact values of our y-intercepts. That will be coming up in different in later lessons, so just hang tight for that concept. I'm going to do one more example on this video, and then I'll start a new one. So right here it's a little bit tricky. I'm just going to rewrite it again. Y equals 2 times x minus 0 squared plus 2. Now the reason why I did it this way is because we know what the p is going to be. P is simply going to be 0. And it's harder to get the x value of a vertex if it's in this form. But like really, I haven't done anything different. This mathematically is the same way. But this right here helps us to kind of understand. Now, never use this as a final answer. All those mathematicians are going to point their creepy little fingers at you and laugh at you. But this is just helpful to take out our vertex. So our vertex occurs at 0, 2. So I'm going to put 1 and 1. And I'm going to say x and y. If I didn't do that above, oh, look at that, I didn't. I should have. -1, Mrs. W, -1. So my vertex is going to be at 0 and 2. And we know that it opens up because the a value is positive. From this, I can actually get my domain and range, because I know since it's going to open up, that's not the actual, but the domain is going to be x is an element of the reals, or in interval notation, -infinity to +infinity, x can have any of those values. And our range is y is greater than or equal to 2x, y is an element of the reals, or if we wanted an interval notation, we would say 2, +infinity round bracket. That means that all of the x values can be are between 2 and infinity. Okay, this one is a little bit trickier because usually we would use our vertex and go over 1, up 1, back to the vertex, over 2, up 4. But this one has a stretch factor of 2. So I'm going to say usually I would go over 1, up 1, but I have to multiply the y value by 2. So I go over 1, up 2 actually. Over 1, up 2. And I can't really capture this, but I would go over 2, and usually I would go up 4, but this time I would go up 8. Okay? So it would be somewhere up there. So I'm just gonna eyeball it a little bit, just so that you understand how that works. So I'm going to do a nice curve. Don't forget your arrowheads. Now, I don't expect you to extend here. Okay. If I give you a graph, I just expect you to graph what's there. But I just wanted to show that extra point. The axis of symmetry is just going to be our x value of the vertex. So x equals 0, because that's the equation of the line of symmetry, which occurs right there. We have a minimum at, because it opens up, a minimum at y equals 2. X-intercepts never touches the x-axis actually, so we say none. Don't write 0 because it looks like x equals 0. Okay, just say none when there are none. And the y-intercept occurs right here. So when y equals 2, or we can put down 0, 2, which incidentally is the same as our vertex.